Here we go with 4.3. If you are in my spring 2020 class and printed this before I made the correction, this is 4.3 and 4.4 that we're going to try to get through today. 4.3, properties of logarithmic functions. Now, because logarithms are the inverse of exponential functions, remember all of our graphing, that means that the properties for logarithms are going to be directly tied to those rules for exponents. So we're going to review our 3 rules for exponents, and then we're going to move those into our properties for logarithms. Product rule for exponents tells me that if I'm multiplying the base, then I add the exponents. For example, in general terms, b to the m times b to the n equals b to the m plus n. As an example, if I'm multiplying 2 cubed times 2 squared, I'm multiplying the bases, and the bases have an exponent. I rewrite that as 2 because the base is the same to the 3 plus 2 power, which is 2 to the 5th power. My quotient rule for exponents says that if I'm dividing the base, because, okay, so multiplication is just repeated addition. Division is just repeated subtraction. So if I'm multiplying the base, I'm going to subtract the exponents. I started to write subtraction there. If I'm dividing the base, I subtract the exponents. My mind is getting ahead of my words. Quotient rule says when you're dividing the base, you subtract the exponents. Here's my general term example. B to the m divided by b to the n is the same thing as b to the m minus n. So let's go ahead and use our 2 cubed divided by 2 squared example. This is going to be 2 to the 3 minus 2 in the exponent, 3 minus 2, because I'm dividing the base, I subtract the exponents, which is just 2 to the first, or 2. Finally, I have my power rule for exponents. When I raise an exponent to another power, that is when I'm going to multiply the exponents. So for example, b to the m power raised to the n power is b to the m times n. So if I have the base written just one time, now up here in my product rule, the base is written twice. I'm multiplying 2 different terms with the same base. Here I only have one base. It is a single term with an exponent raised to another power. This is my power rule where I will multiply the exponents. So that would be 2 to the 6th power. Okay. We're going to use the rules for logarithms to help us expand and condense logarithmic statements to see if we can simplify anything. So we are going to use the rules we're about to get to see if we can expand and condense logarithms in order to simplify. Okay, properties or rules for logarithms. You're going to see them worded both ways, properties or rules for logarithms. The product rule for logarithms. So we talked about the product rule for exponents. Now we're going to apply that same reasoning to the product rule for logarithms. The product rule for logarithms states that the logarithm of a product is the sum of the individual logarithms. Just like my product rule for exponents, multiplication is tied to addition. My product rule for logarithms, the multiplication is tied to addition again. The product is the answer to a multiplication problem. The sum is the answer to an addition problem. In general terms, if I have a product in my argument, right here in my argument of my logarithm, log base b of m times n, then I can expand this to write it as 2 separate log statements. Log base b of m plus log base b of n. For example, let's do an example to show this, how we would expand one and how it could help us. So I've got log base 5 of 25x. Now there's nothing I can do with that as it stands, but I see that in my argument I have a product, 25 times x. Well, according to my product rule for logarithms, that means I can stretch this out. I can expand it to be log base 5 of 25 plus log base 5 of x. Well, there's still not anything I can do with log base 5 of x. But log base 5 of 25, I can simplify. Remember, the answer to a logarithm is always the exponent. And this exponent, log base 5 of 25, what is the exponent of 5 that gives me 25? Well, it's 2, because 5 squared is 25. So this statement simplifies to be 2, and then plus log base 5 of x. Now, I can't do anything else, but I did simplify it somewhat by breaking it apart and expanding it. Let's do one more example here. Let's go back the other direction. Let's start with it expanded. Let's do log base, not like log base, just log of 5 plus log of 2. Now, if it's log log with no base written, we know that that is base 10, or my common log. So I could pull out my calculator, but before you pull out your calculator, let's condense this. I'm adding 2 log statements with the same base. If I'm adding the 2 separate statements, that means I can combine them by showing that the argument is a product of the 2 individual arguments, because addition pairs to multiplication. So I can rewrite log of 5 plus log of 2 as log of 5 times 2. Addition pairs to multiplication. And 5 times 2 is 10, so I have log log of 10. Common log, base 10. What's the exponent of 10 that gives me 10? Well, it's 1. So this works from left to right expanding, and kind of back right to left by condensing using that product rule for logarithms. Now let's talk about the quotient rule for logarithms. The quotient rule for logarithms tells me that the logarithm of a quotient is the difference of the individual logarithms. Difference. The difference is the answer to a subtraction problem. Quotient is the answer to a division problem. So in general terms, log base b of m divided by n is the same thing as log base b of m minus log base b of n. Where I have a quotient in my argument, I can separate that out and expand it to 2 separate log statements by using subtraction. Whatever was in the denominator of my quotient gets subtracted out. Okay, back to an example. Let's do log base x of 9 over x. I've got a quotient as my argument. I've got base x. I can expand this as log base x of 9. There's my numerator. Minus log base x of x. There's my denominator from my argument. Well, log base x of 9 won't simplify, but log base x of x will. What is the exponent of x that gives me x? Well, it's 1. So I can say log base x of 9 minus 1, because this expression simplifies to 1. All right, let's look at our next page. We have a power rule next, the power rule for logarithms. The power rule for logarithms states that the logarithm of a number with an exponent is the product of the exponent and the logarithm of that number. This ties back to my power rule for exponents. When I raise an exponent to a power, I multiply. Power rule for logarithms says that if I have, for example, log base b of m to the p power, I can take that exponent p and I can write it as a coefficient, multiply it out front to my log statement. So I took that exponent and I pulled it out front as a coefficient to multiply it in. Let's do an example of that one. My example of my power rule, I don't have one right now where we're going to simplify, but we're going to, let's see, I want to make sure I don't use one that I would have used down here. So, okay, we'll just do this. We're going to do natural log of 3x squared. Well, here I've got an exponent, but I've also, in my argument, I'm multiplying, so I've got a product. We're going to start there. We're combining 2 of our rules here. We've got natural log, that's base e. So that would be natural log of 3 plus natural log of x squared. Well, natural log of 3 is not going to simplify. Natural log of x squared, though, there is where I'm going to use my power rule. I just used my product rule to split apart this argument. And once it's split apart and I just have a single base for this exponent here, here is where I can use my power rule. So this becomes natural log of 3 plus, and I take this exponent, I pull it out in front. So 2 times the natural log of x. That's all I can do. Nothing else simplifies. But notice I couldn't pull this 2 out here because it's not applied to the 3, just to the x. Before I could use my power rule, I had to use my product rule, split apart those two factors in my argument into 2 separate natural log statements, and then I could use my power rule for the second statement. Let's do some practice using these rules to expand each statement and see where we can simplify. Okay, for the first one, log base 3 of 27 divided by 4. 27 divided by 4 does not simplify as it is. I can't do anything about 3 to what exponent gives me this as it is, but I do have a quotient here, so I can use my quotient rule. A quotient is division. Division pairs with subtraction. So that will become log base 3 of 27, my numerator, minus log base 3 of 4, my denominator. Now log base 3 of 4 won't simplify, but log base 3 of 27 will. What is the exponent of 3 that gives me 27? Well, it's 3. So that statement simplifies to be 3. So 3 minus log base 3 of 4. All right, let's do another. Natural log of 3x squared y. My argument here has 3 different factors, 3 times x squared times y. I can use my product rule because multiplication pairs with addition. So I've got natural log, which is base e, natural log of 3 plus natural log of x squared plus natural log of y. That was my product rule. Multiplication pairs with addition. But then I need to apply my power rule to this second statement because x has that exponent 2. I can use my power rule to bring that out front. So completely expanded, I have natural log of 3 plus 2 times the natural log of x plus natural log of y. That is everything I can do there. Nothing simplifies, but I did get it completely expanded. All right, let's look at number 3. Log base 3 of 9 to the x. I can't do anything with it like it is, but I can use my power rule here to pull that x out front. So I have x times log base 3 of 9. And then log base 3 of 9 will simplify. What is the exponent of 3 that gives me 9? Well, 3 squared is 9. So I have x times 2, which is just 2x. All right, number 4. Log, log, so it's base 10, common log of square root 3. Well, I don't want to mess with radicals as part of a log statement. So we're going to change that radical, that square root, to an exponent. Log of, and then I've got 3 to what power? Well, remember that when I write a radical as an exponent, it's going to be a fraction where the index is the denominator. So this exponent would be 1/2. Square root is the same thing as an exponent of 1/2. So I've got common log of 3 to the 1/2. I can use my power rule. So I have 1/2 common log 3. If I plug that into my calculator, I would do log 3 and then multiply that times 1/2 or divide by 2 or multiply by 0.5, however you want to do that. And I could get an approximate answer of 0.239. Now, this is the only one I could find an approximate answer to in my calculator right now. We don't have any way to do base 3 at this point. These have variables, that has a variable. So that's the only one that I could find an approximate answer for. You'll be told in my math lab when to simplify and find an approximation, when not to. All right, common log of 100x. I've got a product in my argument. I'm multiplying. Multiplication pairs with addition. So this is going to be log of 100 plus log x. Well, log x I can't do anything about, but log 100 I can. This is base 10. What is the exponent of 10 that gives me 100? Well, 10 squared is 100, so that statement simplifies to be 2. So I have 2 plus common log x. I want to encourage you to pause the video, expand these next 4, and then check back to see how you did. All right, number 8 is an interesting one. We've got natural log of e to the 5th minus, because it's a quotient here, natural log of 11. I've got power rule to use in this first statement, so that becomes 5 natural log of e minus natural log of 11. Well, natural log is based e, so I'm asking what is the exponent of e that gives me e? Well, that's 1. And 5 times 1 is just 5. So this simplifies to 5 minus natural log of 11. Again, I have a radical, so I'm going to change that to an exponent. Since the index is 3, the denominator of my exponent is 3, so this becomes natural log of x to the 1/3. And then I would use the power rule to rewrite that as 1/3 times the natural log of x. All right, on 10 through 14, I'm given an expanded set of log statements and I'm told to condense. So I'm using the same properties. I'm just working the other direction. Okay, for example, for the first one, log 25 plus log 4, well, it's base 10 because it's log log, common log. Can't do anything nice with it like it is. So let's use our product rule because addition pairs with multiplication. That means this is the same thing as log of 25 times 4, which would be log of 100. And what is the exponent of 10 that gives me 100? It's 2. So that simplifies nicely where I use my product rule for logarithms. Again, I can use my product rule because I'm adding here. Now, do not get confused. Right here, I'm adding in the argument. I don't have a rule for adding in the argument. That just is. There's nothing I can do with that. I don't simplify this argument where I have addition in the argument. I do, however, need to rewrite this using my power rule as well as combine the two using my product rule. Let's do our power rules first. So power rule first, I would have natural log of x squared plus natural log of x plus 5 to the 1/3. Now I can leave x plus 5 to the 1/3 power, or I could rewrite it as a cube root of x plus 5. Doesn't really matter. Then I'm going to use my product rule here. So I would multiply these two values. Now, if I rewrite this as a cube root, it might make my argument look a little nicer. So I've got natural log of x squared times x plus 5 to the 1/3 power. I can leave it just like that. Or I could choose to say natural log of x squared times the cube root of x plus 5. That's my argument. Either one of these, those are equivalent answers. All right, on number 12, again, I have a power rule. Can't do anything with that. That is an argument where there's addition in the argument. That does not have a rule that applies to that. So I'm just going to use my power rule. So I've got natural log of x plus 6 to the 4th power minus natural log of x cubed. Now I'm subtracting here. Subtraction pairs with division. So I need to use my quotient rule. They're both natural logs, so the base is the same. So I've got natural log of my quotient, whatever I start with goes in the numerator. So x plus 6 to the 4th power is my numerator, and then x cubed is my denominator. Okay, let's do number 13. I have 3 separate statements. 2 of them are being added together, and then I'm subtracting this third statement. So I see that I'm going to need to use my product rule for these 2, quotient rule to put this in the denominator. Each one of them needs the power rule applied. So let's do that intermediate step. Let's say natural log of x cubed plus natural log of y to the 5th minus natural log of z to the 6th. Okay, we took care of the power rule. Now we're going to use the product rule and the quotient rule. The product rule, oh my goodness, tiny spider. I don't know if you saw that run across my paper or not. That I didn't throw anything or scream. Go me. All right, So my numerator, one natural log statement. My numerator is x cubed times y to the fifth, x cubed y to the fifth, and my denominator is this z to the sixth because it's what's being subtracted. So that is condensed. Okay, and we got another long one. This has 4 separate statements. Notice both of these statements are being subtracted out. So in the end, those 2 things are going to go in the denominator. These 2 things are going to be in the numerator. I don't have a power rule to apply to the first statement. I have one on the second, one on the third, and one on this final statement. So let's go ahead and just write this out as natural log 3 plus natural log x squared minus natural log y cubed minus natural log z to the fourth. Again, where I'm adding, that goes in the numerator. Where I'm subtracting, that goes in the denominator. So I have one natural log statement with an argument. In my argument in the numerator, I have 3x squared. In my argument in the denominator, I have y cubed z fourth. Y cubed z to the fourth. And that is completely condensed. None of those simplify. They just are what they are. Sometimes we will use these things and things will simplify, and sometimes it's just practice. Okay, and then we get some more complicated, complex practice problems. 15, 16, and 17 are all a little bit more complex. I don't know how much we're going to be able to do it in the space that we've been given, but we're going to work it out and figure it out. So log base 3 of all of this in the argument. First thing I see is that I have a quotient in my argument that pairs with subtraction. So I know that I'm going to be subtracting out anything in the denominator. In the numerator, I have one argument squared. In the denominator, I have 2 separate arguments. So I'm going to be able to pull that apart. One of them has an exponent there. So let's start pulling this apart. We've got log base 3 of my numerator, x minus 1 squared, minus, and then I have a choice here. I can either write log base 3, you know what, let's just do that. Let's say log base 3 of the denominator, 9z to the 3 halves. So I've got this single statement in my numerator. I need to apply the power rule and pull that power 2 out front. Log base 3 of x minus 1. Can't do anything about subtraction in the argument. It stays. Minus. Now this is going to split apart into 2 separate log statements. This is distributed to both of those so that both of those are subtracted out. What this would look like would be minus, and then in parentheses, log base 3 of 9 plus log base 3 of z to the 3 halves. Since I'm subtracting both of those separate statements, I distribute that negative to both of those. So we've got, next step, 2 log base 3 of x minus 1 minus, now let's think about this, log base 3 of 9. What is the exponent of 3 that gives me 9? Well, it's 2. And then minus, this distributes to there, minus log base 3 of z to the 3 halves. We have another power we need to apply. So 3 halves log base 3 of z. And that is completely expanded and simplified. Okay, you guys do the next one. I'm going to just give you the result of it. I'm not going to show you the in-between step. Those two, we started with a single log statement and we expanded and simplified. This one, we are starting with a list of log statements. We are going to condense and simplify if we can. I'm adding here, that's going to be a numerator. I'm subtracting there, that's going to be a denominator. First step though, I'm going to apply the power rule wherever I need to. So that's going to be natural log of x cubed plus natural log of y fourth minus natural log of z squared minus natural log 8. So next step, single log statement. In my numerator, x cubed y to the fourth, because that's what's being added together. In my denominator, z squared 8, because that's what's being subtracted out. Nothing simplifies. Okay, our last rule for logarithms is the change of base property for logarithms. It allows us to use our calculator to find an approximate answer for any logarithm, no matter what the base is. You know, we only have those two base buttons, base 10, base e, but if we use a ratio, we're able to express our logarithm as a ratio and still find an approximation. Can't get an exact answer this way, but we can approximate it. Ratios work because no matter what the units use, those units divide out. If you think about, if you start with a can of frozen orange juice, the instructions on the can are going to say something like 1 can of juice to 3 cans water. Well, if I didn't want to mix the whole thing for some reason, if I just wanted to make a little bit, I could take a half cup of juice to a half cup of water, or 3 half cups of water, excuse me, 1 can of juice to 3 cans of water. It could be 1 half cup of juice to 3 half cups of water. If I'm doing a cleanser and I'm going to try to get to put it, if I'm doing a cleanser that needs to be mixed with water, it might say 1 part cleanser to 4 parts water. That part can be anything. If I want to just clean my counters, I might do a tablespoon of cleanser to 4 tablespoons of water. If I want to do my floors, I might do a gallon of cleanser to 4 gallons of water. It doesn't matter what my units are, they're going to divide out. The strength of what I end up with is going to be the same. That's my point. So I can use ratios with base E or base 10, and I can get an approximate value for any log statement. In general terms, log base b of m is equal to either common log of m over common log of b, or natural log of m over natural log of b. Doesn't matter which button you use, common log or natural log. What matters is that the argument goes in the numerator and the base goes on bottom. The base goes on bottom. That goes down in the denominator. Let's do an example of this. I want you to use your calculator, and we're going to approximate an answer for log base 3 of 7. Now you can use either common log over common log, or you can use natural log over natural log. What does matter is that you are consistent. You use one button in both the numerator and the denominator. What also matters is that what is the argument here goes on top, and what is the base here goes on bottom in the denominator. When I plug either one of those into my calculator to solve, I should get approximately 1.77 if I round to 2 decimal places. For example, if you look at your calculator, if I do common log 7, and I'm going to close that parentheses, divided by common log 3, close that parentheses just to make it pretty, there's my result. Or I could do natural log 7 divided by natural log 3, and I get the same result. Because it's a ratio, you get those units divide out and it gives you the same result. All right, practice problems. We're going to use that change of base property to simplify or solve. When I use that change of base property to simplify or solve, I'm going to find an approximate value and round my answer to 2 decimal places. Again, it does not matter which set of buttons you use. I'm going to choose to use common log on this one, and then I'm going to choose to use natural log on this one, just to mix it up. So common log here, numerator is the argument, the denominator is the base. If I use natural log here, numerator would be that argument 17, denominator would be the base 0.1. Let's go through and let's plug that into your calculator. For log base 7 of 2,506, you should get an approximate answer of 4.02 when you round to 2 decimal places. For log 0.1 of 17, when you plug that in, you should get an approximate answer of a negative 1.23 when you plug that into your calculator. All right, now this one does not look like what I just did. Number 3 is an exponential form, not logarithmic form. And the variable's in my exponent. I can't solve for x if the variable's in the exponent, but I can use my definition of logarithm, which tells me that if I can write something as an exponential form, I can also write it in logarithmic form. So this would be log. What's my base? Well, my base is 5.44 of, there's my argument, 2.3, and that is equal to x. That is equal to the exponent. I used my definition of logarithm to rewrite my exponential form into logarithmic form, and here I can use my change of base formula. So log of 2.3 divided by log of 5.44, or natural log, doesn't matter. That is what's going to give me x. When I plug that into my calculator, I get an approximate value of 0.49 for x. All right, same thing here. Same thing here. Let's set this up and see what we get. 10 to the x equals 3.91. Can't solve for x in the exponent, so I'm going to use my definition of logarithm. Definition, DEF, definition of logarithm, to rewrite it in logarithmic form. Well, my base is 10. That's my common log. So I don't have to write base 10. I can just say log log of the argument 3.91 is equal to x. And you know what? I don't have to use change of base. It is base 10. I can just use log of 3.91 to solve for x. And I get out an approximate value of 0.59 for x. Number 5, working through it the same way. Definition of logarithm, because I have my exponent has my variable, I have to pull that out. Log of the base, log base 7 of the argument for 10 is going to be equal to x plus 2, because my exponent is x plus 2. So in order to solve this, I need to use my change of base here, and then after I've done change of base, I subtract 2 from that amount. So I'm going to do log for 10 divided by log 7. I'm going to hit enter to get that ratio, and then from that I will subtract 2, and that will be my value for x. Still going to have to round it. I'm going to have to give an approximate value. So x is approximately 1.09.